My subject is the detection of gravitational waves. The first direct discovery was made on September the 14th, 2015. It wasn't announced until a press conference on February the 11th, 2016. I've been embedded in the gravitational wave field since about 1972, about 45 years now. And I was sitting on my sofa when the email came round that said, we've got something that looks like a gravitational wave. Like all the other scientists, I didn't take much notice of it. I just assumed it was another false alarm. But within 2 days, it was pretty obvious that this was something serious. And what it turned out to be was, and this is the title of the paper published in Physical Review Letters, Observation of Gravitational Waves from a Binary Black Hole Merger. I keep pressing the wrong button, I'm very sorry. That is the diagram of what the discovery was supposed to look like. Oh, right, okay, panic. What have I done wrong? The first failure joke. Right, thank you very much. So there we are. There's the diagram that was published in Physical Review Letters of what the actual discovery looked like. Those are the Nobel Prize winners who were announced a little while ago, and the Nobel Prize ceremony is actually on this week. On the left is Rainer Weiss, who got 50% of the Nobel Prize. Barry Barish in the middle got 25%, and Kip Thorne got 25%. I think that's probably a sensible distribution. Weiss was the person who pioneered the technology that actually detected the gravitational waves. Didn't invent it, but he sort of pushed it, interferometry. I'm telling you that now because you'll see it's important later, that Weiss was the guy who pushed the interferometry. That's what we saw, the inspiraling of two black holes and the crashing together of two black holes and the merging into one black hole. And those is an artist's impression of the gravitational ripples coming off the two black holes, and the merger. And it's that was seen. The event took just a fraction of a second. And that is important as well. To see it, you had to see the effect on these interferometers. An interferometer is like this. These ones have arms 4 kilometers long at right angles. And you had to see effects, changes in length of these 4 kilometer arms right down to something like 1/1000th of the diameter of a proton. Okay, to see what that means, that's a photograph of Cardiff Bay. I live next to Cardiff Bay. It's a square mile of water. If you imagine it having vertical sides, it's the effect on Cardiff Bay, the effect of the level of Cardiff Bay of adding 1/1000th of a drop to Cardiff Bay, the square mile of water. The person who made the first attempt to see gravitational waves was this guy, Joseph Weber, commonly known to everybody as Joe Weber. And there's a few of his early publications. There's his book published in 1961. And I think the first time he actually explained how he thought it should be done was at a conference in France in 1959. And that's a schematic diagram that he showed to the conference. And things are still more or less the same today, except that one of these things is a laser pointer, I presume, except that these piezoelectric crystals, which he thought he was going to use and cross-correlate the effects of them, are now interferometers. Then Joseph Weber soon discovered that the great, huge, massive piezoelectric crystals that he thought he was going to use weren't suitable, and instead he used huge bars of aluminium alloy, which you can see there, with piezoelectric crystals glued to their surface. And there you see him working on them at various dates. And that's a schematic of it. You put your big aluminium alloy bar with its piezoelectric crystals on it in a vacuum cylinder, try to isolate it from every external disturbance and measure such external disturbances that are going on. There's a chart recorder which records the vibrations in the cylinder. This is actually one of Joe Weber's early chart recordings, or a photograph of one of Joe Weber's early chart recordings. Then what you do is you get two of these aluminium alloy cylinders a long way apart and look at their outputs, compare their outputs, see where there are coincident peaks of energy, like those three, okay? Count them up, and then you compare the argon trace, which is the bottom one, with the Maryland trace, but you offset the Maryland trace in time, okay? And you look for any correlations between the argon trace and the offset Maryland trace. Yeah? And then you offset the Maryland trace by different amounts. And you continue to do that analysis, and you look at how many coincidences there are with the offset traces, with these various offset traces. They're known as time slides. And you add up all the coincidences you get in the offset traces. Now, the point about the offset traces is that they can only be caused by noise, because there can be no common cause to produce coincident bursts of energy in a time offset trace and the original trace. And then you compare the number of coincidences you've got in the offset traces with the number of coincidences you get in what Joe Weber called the zero delay bin. Okay? And he found some positive effects. One of his assistants, Bob Forward, wrote to a lot of people. Here's his letter of December the 10th, 1969, telling people, if you want to build an apparatus like this, I'll help you. And a number of people did decide to build similar apparatuses. Here's an example of Joe Weber's delay histograms. These are from 1973. And you see the zero delay bin stands higher than the offset bin, the time offset bins. And then by 1969, this is the first positive claim, Joe Weber was telling Physical Review letters, this is good evidence that gravitational radiation has been discovered. However, other people didn't back him up. The people who'd built the other bars did not back him up. The beginning of the end came June the 10th, 1974, at the Cambridge General Relativity Conference, when he was attacked by Dick Garwin, a very powerful American physicist, who said that Joe Weber had no evidence at all, and showed why in a way that convinced most people. Joe Weber had made some mistakes. Nevertheless, this wasn't the end of the story. People tried to improve on Joe Weber's design. And this is an example with the end of the cylinder, the end of the vacuum cylinder open of one of the cryogenic bars. The next generation of bars were cooled down to near absolute zero. There's one in Italy with a man called Guido Pizzella standing in front of it. There's one in Louisiana with its founders. And there's three of the cryogenic bar people talking about the fact that they were going to announce they'd found something at the immediately upcoming conference. That's just them standing in the doorway of the conference room, which I photographed. And about half a dozen announcements to have found gravitational waves were made over the course of this resonant bar period. Blimey. Sorry, it's the 5-minute time that's caused me to say blimey. But all dismissed. This is Joe Weber, a photograph I took of him in 1993, and a paper he published in 1996, claiming that there were correlations between the gravity waves he had found and gamma ray bursts, another cosmic mystery. This is very interesting. I went around all my buddies in the gravity wave business saying, what do you make of Joe Weber's latest paper? And it turns out I was the only person to have read it. So that is how low Joe Weber's credibility had fallen by 1996. These are the interferometers, hundreds of millions of dollars now. This is a kind of story of how Weber, on the top left-hand side, was dominant in the early 70s. By the early 80s, cryogenic bars were dominant. By the early 90s, interferometers were taking over. And by the early 2000s, it was more or less only interferometers with a few cryogenic bars still running. Two things I want to show. You see, I haven't really started to talk yet. One, Joe Weber inspired the attempt to build devices that could detect gravitational waves directly. Two, I'm going to try and do a bit of counterfactual history. Very suspect, so watch this carefully. And the counterfactual history is that without Joe Weber, we would not have seen gravitational waves at all, and might not have seen might not see gravitational waves, high-frequency gravitational waves for the foreseeable future. Let me try and establish that. Ray Weiss, remember? The dominant Nobel Prize winner, tells you here, you haven't got time to read it, that it was Joe Weber who got everybody going on trying to find gravitational waves directly. Now, gravitational waves, that's a repeat of the graphic I showed you before of the inspiraling inspiraling black holes. But these black holes have been slowly spiraling towards each other for millions of years. Okay? And we know that they're there. We already knew that they were there because Hulse, Taylor and Weisberg had studied a binary neutron star whose orbit was slowly decaying. They watched it over a decade or so and discovered that its decay exactly fitted in with the emission of energy through gravitational waves. So by the early 1990s, we knew that these systems emitted gravitational waves early in their lives, and we knew that there were lots of them, lots of binary systems emitting gravitational waves early in their lives. Okay. What we didn't know was whether there were any sudden and intense bursts of energy from the final few seconds of the in-spiral. We didn't know that, but that was what this mad detection program started by Weber was supposed to see. But we didn't know there was anything there. But we did know that there were lots of instances of these much more weak waves coming from early in the life. And there was an idea for directing them with a gravitational wave detector system of satellites in space called LISA, which is there. It has a 5 million kilometer baseline, okay, and it can integrate the signals over a long period because the signals last a very long time, and that makes it extremely sensitive. So LISA, if it worked, had to see something. Joe Weber's system for seeing the last moment of the in-spiral, we didn't even know if there was anything there. And as Weiss said, it was Weber who got people even to look at these high-frequency waves and the possibility of them. Without Weber, they wouldn't have done it. Peter Bender, who started the thing called Lagos, which was the pre-runner of LISA, told me that it was Weber who inspired him. I don't know if that's true or not. I'm going to have to go very fast, obviously. My claim is Weber caused the impetus for the search for high-frequency waves. Weber may have caused the impetus for any kind of search. If Weber, it wasn't the person who inspired Bender, it's almost certainly that the much more sensible satellite program would have happened, and not the stupid, crazy high-frequency detection program. That's all written up in my 2 books. There they are. And this is my conclusion that'll delight Stuart. Science is a stranger thing than it is usually thought to be. Here we have a widely acknowledged and widely scorned failure, often taken to be a huge embarrassment to physics, without which, according to my counterfactual argument, there would have been no success. Thank you.
Well, thank you so much. I want to thank the organizers. It's a real pleasure to be here. I will save most of my failure jokes until they come up spontaneously, but there will be some. Anyway, my name is David Kaiser. I teach at MIT, and I'm delighted then to build on many of the remarks that Harry just shared with us. I was trying to think about what might be an interesting way to try to frame some ideas to maybe spark some discussion in not a huge amount of time. So I decided to be rather parochial. If I'm going to fail, I'm going to fail on my own terms. So I wanted to sort of cherry pick some examples from the history of modern physics over the last roughly century or so, and see if we can discern some useful patterns in types of errors which might lead to interesting comments on failure. The first type of error I wanted to put in front of us is not the usual sort of type 1 or type 2 error, false positive, false negative, that many of us might think of in terms of scientific errors. It's really more a question of how would we ever notice them. This is a plot that I like to call Death by Physical Review, a photograph rather. Physical Review, the main workhorse journal of research in the field published by the American Physical Society. The journal began publication in 1893, and shown here are the decadal stacks of the journal. So here's the 1890s, 1900s, 1910s, 20s, 30s, 40s, 50s, 60s, 70s. By the end of the 1970s, there were enough physical review journals just in that decade to kill a person, right? This is actually death by scientific publication, publish and perish. And there was a running gag in the 1950s, back when the stack had already really begun to take off. A question often asked of PhD students in physics for their qualifying exam: given the rate of acceleration of publication in the field, when will it be that the covers of a single year's journal will recede from each other faster than the speed of light? Because that seemed like a real possibility, that publication might break relativity. A bit more sobering is not just the volume, but in fact, how much of this is going to never, ever, ever be seen by any human ever again? And the answer is an enormous amount. This is an analysis that itself is now 20 years old by a physicist named Sidney Redner, who's a physicist at Boston University and is very interested in a field called scientometrics, very active there. So here's an analysis that Redner published about 20 years ago. Among the things he did is he took all the scientific articles that have been cataloged in what we would now call the Web of Knowledge, the Science Citation Index, or Web of Science, it was called for a while. So he took all the scientific publications cataloged by that process, published in the year 1981, and traced all of citations to those articles over the ensuing 16 years, and found that almost half of the articles that had been published had never been cited once, even by their own authors, in the next 16 years. And so that is a reminder that the first type of error we have to think about is simply just, what are you even going to think about? What are you going to even focus on? What's going to grab our attention? Because so much that's happening is neither right nor wrong, but perhaps simply irrelevant. Okay. There's another type that historians and philosophers and sociologists of science have often talked about. Sometimes it goes under the title pathological science. This is a well-known article, really a lecture that was given by the industrial physicist Irving Langmuir in 1953 and republished many times over the years. I'm going to call this not pathological, but simply wishful thinking. And this is an example of types of claims that have been made, even just, let's say, within physics, so it's not limited to that. Of sort of surprising effects that seem to be just at the edge of detectability, for which the researchers often have very strong reasons to expect to find something, and at least in Langmuir's analysis and many others, can sort of fool themselves not by being acting improperly, but simply sort of wishing and expecting there must be something there to see, and then in some sense over-interpreting or pushing beyond what might be a reasonable expectation given the types of instrumentation or otherwise. And then, although sometimes these effects are often seen by many other researchers, before too long, many groups fail to replicate these things, and then the pathology in Langmuir's analysis was what the original researchers did in response. Did they sort of calmly and soberly take the constructive critique of their colleagues, or did they dig in their heels and invent ad hoc reasons why they had been right all along? One of the first examples that he wrote about, a kind of chestnut in the field, something called N-rays, discovered by the French physicist Blondelot at the University of Nancy. I think N was in honor of his hometown, Nancy, in France. This was first announced to the scientific world in 1903 by Blondelot, and then a series of publications, many of them then translated into English and so on. And this was not, on the face of it, a crazy thing to expect. This is just a few years into the very heady excitement about radioactivity, strange emanations or radiations that had no prior explanation. And Blondelot thought he'd found, frankly, the next one, and what many people thought would be a series of these. It turns out when people began not to be able to reproduce these, a kind of enterprising kind of cowboy physicist went to go inspect this and was concluded that Blondelot had really been sort of fooling himself, that he was not adequately dealing with scientific controls or shielding or over-interpreting pretty mediocre evidence. And this became a kind of cautionary tale for seeing what we want to see. Blondelot was never accused of having done anything. It wasn't fraud. It wasn't intentional misrepresentation. It was simply wishing to see things that maybe weren't really there. I'll say very little about Joe Weber's case. We just heard that wonderful presentation from Harry Collins. And I just want to say, you can't quite see it from this flat projection. I do encourage you to read Harry's book, one of his many books on this. What you can't tell from this slide is the book is about 900 pages. It's not only about gravity, it is a significant source of gravity. And I want to thank Harry. I've learned an enormous amount from Harry's work on this over many, many years. And so, again, I think as a similar example, as you saw, the successful detection of this phenomenon has taken $1 billion and 1,000-person group spread over many, many areas of the world. with these machines that are 4 kilometers on a side, and Joe Weber was jump-starting this effort with a machine on the order of 2 meters long. So something else had to give, and yet Weber was quite convinced for a long time that he had seen the real thing, increasing skepticism notwithstanding. Sticking with gravity waves for a moment, a kind of heartbreaking episode for myself. Much more recently, this was an announcement by the BICEP 2 collaboration back in March of 2014, fairly recently, where they had built this really pristine instrument on the South Pole. It's in Antarctica, really right near the actual pole. And they were searching for a different sort of gravitational wave that would have been generated by by well-motivated ideas about the very early universe, the moments just after the Big Bang. And there should have been a remnant left over of that other form of source of gravitational radiation that might just have been barely visible in certain very subtle patterns in something called the cosmic microwave background radiation. And again, this was announced to great fanfare, but within about 12 to 18 months had to basically be walked back, that they had been a bit too hasty in not taking adequate account of certain compounding signals, foregrounds, that other groups hadn't quite released all their data on and so on. So again, no signs of chicanery. There is a story here about the rush to be first with Nobel Prizes in line, but again, sort of over-interpreting beyond what the data themselves really, I think, could reasonably have been expected to show. Now, there's another category that historians and philosophers and sociologists of science have studied, and that's actual fraud. The challenge here is that many characteristics of fraudulent claims look a lot like the wishful thinking ones in terms of at the edge of detectability, not always easy to replicate, expectations to find something there that, although the claims might be a bit over hasty. Famous case that broke around the year 2000, 2001 from Jan Hendrik Schön, an experimental condensed matter physicist working at Bell Labs. There's a really marvelous book about this episode by the science journalist Eugenie Reich I recommend to all of you. And here's an example. I just want to pause on this for a moment. I've learned from Eugenie's book. Here's an instance where peer review actually sort of accelerated the fraud instead of tamping it down. Schön, it is now clear, was just manufacturing, often whole cloth, the data he was reporting and getting published in some of the most prestigious scientific journals on the planet, Nature and Science, Proceedings of the U.S. National Academy of Sciences, Physical Review Letters, and so on. And what happened often was that he would make a fantastic claim, submit it for peer review, and the reviewers would often say, well, if that's really what you think, then I would expect to find the following ancillary things in other systems, or have you checked for this, have you looked for that? And he'd say, that's great, and then would respond, having made up responses to exactly match what the peer reviewers said to look for. So here's where peer review actually helped sharpen what turned out to be something like 36 papers that had to be retracted from the most selective journals on the planet. And I'll go, in the interest of time, I'll go quickly over a similar story that broke around the same time, around 2001, of a claimed detection of heavy elements beyond the sort of naturally occurring elements on the periodic table, heavier than uranium at atomic number 92. And here's an instance where, although there's some dispute over who likely did this, I think all parties agree that some member of this team at the Berkeley National Laboratory used a text editor and simply input data by hand to make it look like certain radioactive interactions had been detected by the machines, literally putting in fake data from scratch at the edge of detectability for an effect that many people expected to find, and so on. There's another category I've spent a fair amount of time thinking about in my own historical work. I like to think of them as productive mistakes. Here's a piece I wrote with my friend Angela Kreger, who's an historian of life sciences. We wrote for Scientific American, but it really I've been running through this in many of my other historical writings as well. These are mistakes, I think, much like what Harry was getting at just a moment ago. Examples that are clearly in error when taken on their face, and yet had an enormous productive, heuristic, generative role. They were wrong, and yet by finding out how and why that instance was wrong, the entire community turns out to learn a great deal. Here's one example. Harry mentioned the Nobel Prize ceremony is coming up very soon. One of my favorite examples is when the great Italian physicist Enrico Fermi received the Nobel Prize in December of 1938. He actually used this to escape fascist Italy and came to New York and taught for many years at Columbia before moving to Chicago and working on the Manhattan Project. Leading figure. He received the Nobel Prize and for work that his group in Rome had done that seemed to show they could make elements heavier than uranium by bombarding certain nuclei like uranium with neutrons. The neutrons would sometimes be absorbed, then they could undergo a certain nuclear reaction, a beta decay. A neutron could transmute to a proton, move the whole nucleus one step up the periodic table, and so on. This was enormously exciting, and indeed was deemed Nobel Prize worthy. What became clear just as Fermi was basically on the dais in Stockholm receiving the prize was that his group had almost certainly not seen what they thought they saw. What they had almost certainly done was induce nuclear fission, splitting these very heavy nuclei apart into much smaller portions rather than actually stepwise moving up the table. So he got the Nobel Prize in error. On the other hand, because the group had pioneered the phenomenon, the techniques, what to look for, how to study it, this really moved the entire field forward with a great deal of enthusiasm, so that in rapid order, many other groups working in this vein were able to find what became the leading account of these reactions. Again, in the interest of time, I'll go quickly here. An example I looked at in some more detail is from the 1950s and 60s, leading particle physicist Geoffrey Chew, who really wanted to sort of redo how physicists thought about fundamental interactions among elementary particles. And again, it became clear even by the early to mid-1970s, many of the particular claims simply wouldn't hold up, and yet the wealth of theoretical tools, the wealth of ideas about how to analyze these very obscure interactions, had a kind of unexpected second life, and in fact are often incorporated in leading ways in the very theories that he was hoping to replace. So there's a kind of technology, theoretical technology, that turned out to be enormously generative, even though the core claims didn't always stand up. I wrote this book called How the Hippies Saved Physics. Similar kind of story, although this one involves more naked hot tubbing. The group called themselves the Fundamental Physics Group, also based in Berkeley. They were very playful. They were sort of wrong much more often than they were right, but they were pushing and pushing and pushing at this sort of curious boundary between two of the most important pillars of modern physics, quantum theory and relativity. And they kept trying to do things like design machines that could send signals faster than light using obscure quantum mechanical ideas that seemed to butt up right against the rules from relativity. They were wrong every time, but in the process of showing why each new device would fail, the entire community learned enormously consequential features of the structure of quantum theory that no one on the planet had known before. And in fact, this is now really the bedrock for a multi-billion-dollar industry in quantum encryption, quantum computing, and so on. So the fact that they were wrong was actually incredibly important to find why they were wrong and the very subtle reasons behind those mistakes. Lastly, I figured, why not show up to a conference on failure and say the biggest failure we have is actually Albert Einstein. I say that with only modest tongue-in-cheek here. So Einstein gave us many, many things that we still rightly celebrate, but for the last 30 to 35 years of his career, he really went off on what even his contemporaries considered a series of kind of not very productive blind alleys, his efforts to find what would be called a unified field program. And here I think we can say that unlike those productive mistakes, he kind of took himself out of the race. He stopped working at this interface to try to bring together interesting, successful areas of physics and see how the puzzle pieces might gel, and in fact was sort of willfully ignoring, refusing to engage with whole swaths that had been successful. So this seems like a failure. I think it's, at least we can discuss, is that what we mean by failure? Whereas these other errors, these other mistakes, turned out to be remarkably generative and productive. So let me wrap up. Some implications for failurology. The first, let's keep in mind, there's just an enormous, I think, terrifying volume of scientific material being published that might be right, might be wrong, but is most importantly totally irrelevant to all humans. And that is just a very sobering fact. Number two is a question of teleology. I think the organizers raised this in the write-up ahead of the conference. Are we always only going to be able to recognize these things with hindsight? We can say that some of these clear mistakes that were clearly, claims that were clearly in error, we can recognize they had a kind of productive knock-on effect with from some distance, with some historical remove. Is that true? Is that the only way to identify these productive mistakes? Do we always need hindsight? And likewise, are failures simply mistakes that haven't yet turned out okay? Coming again with this notion of the flowing downstream, is the difference between a failure and a productive mistake simply a matter of time? Might Einstein's hoped-for vision indeed turn out to be a pot of gold after all? And so those are the questions that I look forward to talking about with the group, and I thank you again. Thanks.
Yeah, thank you very much. I'm very pleased to be here, so thanks for the invitation. My postdoc, Nora Hangel, and I spent several months analyzing interviews that she had conducted with a number of scientists. In these interviews, scientists didn't have many positive things to say about failure. They tended to associate failed project with personal failures, and especially early career scientists worried about future unemployment. When you Google failure, you will find a lot of motivational wallpapers that tell us that failure is actually something that we should embrace and it's a good thing. So that is more in line with the conference theme. And what I want to do in my contribution is I want to suggest that studies of actual scientific episodes can do an even better job in reassuring the scientists and maybe preparing them for life, as was mentioned earlier, than these motivational wallpapers. So they can tell us more about what failures actually are. Now, I would like to illustrate that with just one example from the early history of bacteriology. So in the mid-19th century, that is prior to the big medical investigations of bacteriology. So I want to look at botanist Ernst Hallier's theory of pleomorphism. It was called retarding advancement. It was called a pure fantasy, fortunately refuted. It was called an absurdity, and even recently somebody talked about Hallier's murky implications. So we can see in the eyes of the commentators, it seems to be a rather big failure. Now, when we look at the actual historical situation, so these questions arise. What kind of failure was this? What, if anything, did 19th century bacteriologists learn from it? And what, if anything, can we learn from it? So, just a few words on bacteriology prior to the 1880s. So that was a time when bacteriology was part of botany and zoology rather than medicine. And researchers, predominantly microscopists, debated almost everything about bacteria, what they were, whether they were plants or animals, and how they could be classified, how they developed, what they ate, how they slept, what food they consumed, what effects they caused, and so on. So everything was kind of in doubt. So the idea of pleomorphism is a particular theory about how different bacteria relate to each other. So it's the idea put forward by Hallier and other people that there exists a basic fungal entity, a so-called Pilzwesen in German, which can grow into different morphs. So it can grow into fungi, into yeast, and into molds under changing environmental conditions. So depending on the environment, this Pilzwesen, this entity, grows into different things. And each of these morphs causes fermentation. And that is, again, a very wide term that can mean alcoholic fermentation, can mean it produces sour milk, putrefaction, and also various kinds of diseases. And what you see in the corner there is a picture, not by Hallier, but by Thomas Henry Huxley, which kind of illustrates that everything is basically related to everything. So what is interesting about Hallier is that he was trying to develop experimental techniques for the investigation of that approach and for the testing of his ideas. And he developed two methods and two technologies, actually. And he said they both need to be combined to study pleomorphism. One is that we need to trace the development of one particular organism, so one particular Pilzwesen, through the different stages to kind of confirm this idea of development through the different morphs. And the other one is to examine the products of fermentation of the particular kinds of microorganisms to show what kind of things they produce. And here are the technologies that he he developed. So on the left side, that is the apparatus for the study of development. So you can see that this is this glass sphere with a culture dish underneath, and that helps you to both keep the air clean, and then this glass thing, this glass dome, can be lifted so that you can use your microscope to investigate various stages of development. The other apparatus is to study the process of fermentation, where the point is that you have to make sure that nothing from the outside gets into your culture and contaminates it, because you want to establish what the product is of this one particular kind of organism that you have under observation. So he suggested these kinds of technologies to confirm his notion of pleomorphism, and unfortunately they didn't work, which from the perspective of today we can easily see why, because they did not what they were supposed to do. First of all, it was impossible to just keep one organism under observation and follow it through the different stages. And the other thing is that the apparatus just didn't keep contaminations out of the samples. So the thing is that better technologies could not be developed at the time. So people were, in fact, it's only recently that biologists have the technology to study development in the way that was envisioned in the 19th century. And it also didn't work to keep the cultures clean. So these two apparatuses did not do what they were supposed to do. And what is interesting is then there was another bacteriologist at the time who developed an interesting alternative, namely a physiological classification of bacteria. So he agreed with Hallier that bacteria are too small to be classified, which you can kind of see on the plate on the right side, because this is what you see with a microscope. You can't really distinguish these little dots. But Ferdinand Kohn and his co-workers suggested that bacteria can be classified by function. And so they distinguished three different types of bacteria. The first one producing colors, the second one producing fermentation, the third one producing disease. And what is interesting here is that they picked the first one to investigate because you could see quite easily with a microscope what kinds of colors these bacteria produce. So the idea is that regardless of the environment, you could see that the same types of bacteria always produce the same colored pigments, and on this basis you can actually produce a classification for different bacteria, but according to a very different principle. We are no longer classifying by form, we are classifying by physiological function. The other thing that I think is also important to notice is that this classification was not complete because, again, for the bacteria producing diseases, no real classification system could be found at the time. So this was a new approach to the same problem. Now, what exactly can we learn from these two examples, or rather from this one episode, for our conference theme? So the question is, was pleomorphism really a failure, and if so, in what way? And I think what we can see here, I should say that I'm, of course, generalizing over one example, but I do think that this is a fairly typical episode in the history of science. So what we can see here is that the debate at the time, when we look closely, turned out to be very complex and multifaceted. One thing that I think is interesting here, this is kind of in line with the typology that we saw before. I think when we look at these kinds of failures from this history of science perspective, it's very important that we distinguish between different kinds of failures. So failed theories, failed methodological approaches, failed implementations of approaches. And when we use that to look back at the episode, we see that the experimental tests of pleomorphism turned out to be impossible with the technology available at the time. The theory as such remained an option, not only for Hallier, who continued to believe in it, but also for many other people. I already showed you the plate by Huxley, which was several years after Hallier did his experiments. Hallier's observations inspired contemporaneous theories of wound infection because he saw bacteria everywhere, and that was actually something that other people took up to say, well, you know, they might play a role actually in some medical conditions. And then finally, the methodological principles, and I think that's really an important issue, the methodological principles of causal experimental research that Hallier took for granted were never contested. So it is the implementation of a certain technological approach that really failed here. So in fact, I think we can say that by these different approaches that I presented here very briefly, the methodological principles of causal experimentation were in fact confirmed. So let me see. When we look more closely at the historical situation, Hallier's scandalous and absurd failure doesn't seem to be such a spectacular failure after all. It's certainly not a retarding advancement or pure fantasy, unfortunately refuted, absurd, and so on. But the interesting thing is when you look at the way in which that judgment came about, you can see that at the time, one of the opponents of Hallier, who had a different theory, put forward this judgment, namely it was absurd, there was a pleomorphic extravagance, and it belongs to the scientific chronique scandaleuse. That was in 1887, 20 years after Hallier, and I think we can see that many people just kept referring to that without looking at the actual situation. So, what, if anything, did the 19th century bacteriologists learn from Hallier's failure? This is something that I think we will discuss. I think that they did not learn from the failure as such. Even though it was clear that Hallier's technology was not working, just by staring at the technology, you can't really find a way forward. So I would say that just as there is no royal road to discovery, there's also no secure path from failure to success. So my last kind of concluding slide, what I think we can do is we can learn from studies of scientific episodes like the ones I presented and like the ones that we've seen earlier. We'll usually find that the big failures, the so-called big failures, will turn out to be multi-layered, very complex events. We will also find something that I couldn't really show here in much detail. The day-to-day research practice involves numerous dead ends, detours, failed trials, partial successes, and delayed effects. And that kind of leads to my last and final message, namely that studies of actual scientific episodes can be extremely instructive, I think, if we pay close attention to the tools and practices of knowledge generation, not just the results, and if we consider why past commentators may have been inclined to be critical. And finally, trying to present a historical episode in less than 15 minutes defeats the purpose. Thank you.
Hi, everybody. Thanks for coming out so early in the morning. I I have to say it's a daunting task to listen to several talks and then suddenly generate some intelligent commentary about it, so forgive me if this is a bit jumbled. But I greatly enjoyed all of the talks. I thought Harry gave a really interesting story of success in the terms of scientific breakthrough built on a series of failures in history, or initial failures in history. And I thought David and Jutta both gave us a really interesting unpacking of what failure means in science, right? It's not just one type of failure. There's, in fact, a broad typology of errors. There are many ways to fail, right? As Stuart said, many ways to be unhappy. And I think that's really critical for thinking about what kinds of failures are good, what kinds of failures are bad, and how can we sort of push on making those good types of failures versus falling into the trap of making negative failures. So I just wanted to pose a few questions, some very general ones, and one or two aimed at education in general, since I come from science education and educational psychology. So one is kind of, when do you know as a scientist when it's time to keep going and when it's time to call it quits? So when have you made a bad type of failure, right? For example, the wishful thinking type of failure that David talked about. And how do you know when you've made a really productive failure, right? Something that science is going to learn from in the future. And, you know, me being a kind of social scientist, right, for instance, I've been given the advice that to be a good scholar means you have to be kind of stubborn, right, and develop a thick skin. And even though you get negative feedback from reviewers when you submit your papers, you have to still keep working on those ideas, right? But some failures are actual failures, right? And signify that it's time to maybe stop an area of research or change the way you're studying something. So how do we know as scientists and scholars as well, when it's time to keep going and when it's time to call it quits? And then a second question, again, which I think is related, is I think David talked really nicely about positive kinds of failures and negative kinds of failures, right? So how do scientists learn to avoid those bad types of failures? How do they know when they're a bad failure? And how do they learn to push on good kinds of failures and productive mistakes? We have a term in education called productive failure, which was put forth by Manu Kapoor, and it's this whole instructional method where kids are pushed to solve a really complex problem where they're going to fail. But in that failure, it's prepares them to learn from later instruction, right? So it helps them activate prior knowledge and identify knowledge gaps and begin to think about what kind of are the features that are critical to look at before going on to then, for example, receive a lecture about a scientific concept. And those kinds of productive failures, right, are actually good for learning. So I'm interested in sort of identifying those kinds of productive failures. And then a third question is sort of what can we learn about education, or what can science education take away from these stories of scientific failure? So more broadly, I'm interested in what kind of message would you give to kids and teachers who are learning science and learning that there are many failures that occur in science. What can they learn about the process of how science is done? And what should they take away as a message of how to build on these failures? So, for example, in the past 20 years, there's been this big movement in science education away from what we call cookbook science, right, where you kind of give students an experiment to do a priori. You tell them exactly what steps to follow in doing the experiment. The result of the experiment is predetermined by the teacher in the textbook, right? And there's kind of a canned solution that students are supposed to determine, and this predetermined knowledge the teacher is essentially dispensing out to the students. And we've been moving away from cookbook science to more authentic inquiry, right, where students are learning that the goal of science is actually to generate knowledge, not just to guess what the teacher wants you to learn or demonstrate what's in the textbook. Sorry, I'm going over time, so I will stop. Anyhow, so what can we learn about authentic inquiry and the process of dealing with failures from this history of science that you've talked about? Thank you.
I enjoyed the talks very much also. I love this term, failurology. I think it's new to me, and it's something that I'm going to pass on to my students here at Columbia, teaching them how to write about science in real time, without the luxury generally of hindsight. How on earth are we supposed to cover each piece of scientific news, given the extensive ways in which failurology shows us that the story is more complicated than it generally appears in the paper and then in the press. That lovely slide that David opened with of the locomotive that's gone off the tracks, that kind of failure, journalism is very, very good at covering. And in fact, I remember with the Exxon Valdez oil spill, the Exxon PR people's defense when they were getting this maelstrom of press around the world was, why is the press so interested in this failure? Why don't they focus on all our successful efforts to transport the oil? Why do they have to focus on our failures? Well, the answer, I think, is obvious with the locomotive and obvious with a Titanic oil spill. But how do we cover, how do we communicate the process of science better when all of the incentives are perpetually to celebrate, immediately to celebrate, whether that celebration is warranted in the long run or not? So I think this is just incredibly useful to be looking at these case studies and to be thinking about failure systematically. And I'm really looking forward to learning more from all of the speakers and then trying to pass that on. And I just want to add one more category, meanwhile, to failurology, which is the failure to communicate. Many times, in hindsight again, a breakthrough is made and fails because the discoverers fail to communicate it properly. And the classic example here in the history of science is probably Oswald Avery at what was then called the Rockefeller Institution, who discovered with two younger colleagues in the 1940s that, contrary to all expectations, the molecule that carries genetic information is DNA and is not a protein. And he had a lot of trouble getting that idea across. So my time is up, but that was a failure in communication, not a failure in the apparatus, as Jutta points out is so frequently the case, or a conceptual failure. And that deserves to rank among the primary examples of in failurology. Okay.
Thank you so much. I just wanted to give the speakers a chance to say a couple words if they have any comments on these two sets of very interesting questions. Yeah, Harry, please.
Okay, is this working? Yes. Yeah, okay. Just, one thing I want to suggest that you should be very, very careful of is I'm not sure that you can learn much from what we've said up here. Because the point about failurology, nice neologism, is that it's a retrospective discipline. Nobody knows or thinks they're failing at the time they're failing. I mean, the frauds aside, but I don't think the frauds really belong in this typology proper, okay? So Max Planck's, I don't know if it's true, David will tell me whether this real, and Jutta will be able to tell me whether he really did say this, but he's supposed to have said, science advances funeral by funeral. In other words, nobody ever gives up their view until they're in the grave. I'm not quite sure what happens when they're in the grave, but they certainly don't do it by then. And I think that's true, and I think it's the right thing to do. Yeah? Everybody was trying to persuade Joe Weber once, after 1975, give this up, Joe, admit you were wrong. And Joe Weber would never do it. And Joe Weber went to his grave in the year 2000, still believing that he had seen high fluxes of gravity waves. And I found him a tremendous inspiration. And, it's one of the things I've done is I stick to what I think, irrespective of what everybody's telling me. And I think that's what science needs, okay? There is a more difficult question. And the more difficult and relevant question is, what do other people do? So a number of people had to decide whether to try to repeat Joe Weber's early experiments. And Joe Webber had to work very hard to make his results credible enough for other people to put the time and energy into the work to repeat it. That's where the real question of failure lies. Do I spend time and money, especially if it's an empirical investigation, on doing the same as that other guy has done to prove him either right or wrong? And that is an incredible decision, and it's really worth this. I think a really good research program would be to investigate how those kinds of decisions are made.
Well, and also, if those are taxpayer dollars, whether those decisions are the right decisions. Other responses?
Well, sure. So I'll try to be brief. Is this microphone on?
Yeah.
Yes. Okay. Good. Thank you. So thank you to the discussants. I think we'll have a lot of fun chewing on these themes over the next 2 days, not just this morning. I do want to pick up something that Harry was just saying, though, and that's that even if we might log the kind of bravery, or if not stubbornness, of some of these people who are at first, who refuse to back down in the face of constructive or not so constructive criticism, I do think we have to be cognizant of effects on entire fields. And it's something that I've learned, actually, frankly, from a lot of Harry's work in the gravitational wave case in particular. Fields can develop a kind of bad reputation, or is often called a kind of odor. And so if someone is simply not backing down, will that actually eventually lead to blocking progress in the field because the field takes on a kind of taint? That's something I've been very interested in with the work on the hippies that Harry also knows quite a lot about from the 70s. Whole fields can be in or out of favor, whether that's with program officers at a federal agency or fellow researchers or journal editors, whatever. And I think the kind of psychological, sociological, delicate balance between sticking with your guns and kind of veering into a kind of pig-headedness has an impact beyond the career of one individual. And that's where I think, again, empirically speaking, historians and philosophers and sociologists can and have investigated these questions beyond the role of one laboratory, one researcher. But I think we do have to look at a kind of larger ecosystem, especially, as Pamela reminds us, I mean, LIGO costs more than $1 billion. You know, it's hard to fail very often with that kind of stakes on the line. Put it that way.
I wanted to say a few words related to the points that have been raised about education and communication. And I think, so what I said very quickly at the end, I think there is something there that might be helpful for education that I've actually tried in my own teaching of science undergraduates. When you look very carefully at the generation of knowledge and really look at the details, that's where you will find things that go wrong, or people who don't really know what to do next, and these kinds of things. And I think when you look at the way in which science is communicated in, say, the popular press, it's usually focused on results, not on methods and how science really works. This is why I now call my course "How Science Really Works." And what I found is that science students don't know that, and that is really interesting because that's not something that they learn in their undergraduate science education. They don't have the vocabulary to talk about these things, and they also, I mean, many times they just do experiments. Well, they are given certain things that they should do. So this kind of an inquiry-based learning, which includes failure or doing things wrong or not getting things to work, that really, I think, is something that undergraduate science students don't experience, and they can't talk about it either.
Can I just say, from the perspective of the history of science as well, I'm a historian of science of the early modern period, and I really think that I do exactly the same things in my classes, because a lot of people talk about science literacy as the knowledge of content, right? But I actually think science literacy is about how science works. And one of the ways that science works is, of course, communication. It's a whole endeavor, right? It's a whole huge enterprise that's moving along in a really unprecedented way since about the 1940s. And in, you know, all nations that want to develop, et cetera. So understanding this whole enterprise of science and how it works is, I think, the way that we can get around the simplistic view of science in the in journalism as well as in education, and you know, the people who study science in that detailed way are historians, sociologists, and philosophers of science. And so I think that bringing that expertise into science classes and to science students could actually inform them about failures of all kinds, but also just about the enterprise that science is. Any other points? If not, we'll move to audience questions. So please go to the microphone. If you want to ask a question, please go to the microphone.
So it's not a question, it's a comment, because especially because there was this question about...
Could questioners just say who they are?
Yeah,
please?
I'm Mario Livio, I'm an astrophysicist.
Thank you.
Especially there was this question asked about how do you know when to stop and so on. So unfortunately, I don't think there is a very good answer to that. And the reason I say this is that in the history of science, we have had all kinds of people, and sometimes even within the same person. So I want to just give a few examples. So David mentioned the BICEP 2 result. So the BICEP 2 result is this experiment, incredible experiment at the South Pole, which claimed to have discovered these B modes, which is the sign of inflation. What happened was that, you know, later results, especially by the Planck satellite, showed that all of that was probably the result of just seeing dust. Now, the BICEP 2 people accepted that. So this is an example where the entire BICEP 2 people, they were actually co-authors on the paper that said that the result came from dust. So they accepted that this was actually a mistake. At the same time, one of the greatest astrophysicists of the 20th century, Fred Hoyle, had a wrong model which did not have a Big Bang. It said it was a steady state. And he did not abandon this model till the day he died, in spite of increasing continuous evidence for that a Big Bang occurred. Now, he was so smart that he could always invent yet another way of how he can explain the new results. So that's a counterexample. Now, there is one person, Linus Pauling, who actually showed both trends. In the case of, you know, he had a model for the triple helix for the DNA, and within a few months later, he accepted that Watson and Crick got the double helix correct and that his model was wrong. He accepted that. On the other hand, everything he said about vitamin C, he did not accept till the day he died, even though all of that was completely wrong. So even within the same person, we see the two tendencies, and certainly within the community at large, we see this. So there is really no very, very clear way to say, you know, when to stop and what not, unless, you know, there are these cases where, you know, you have a result from an experiment, there are 100 other experiments that show that it is wrong and so on. Okay, this may convince people. But usually it's like Harry said, it's by funerals. I mean, the people who hold the old ideas, they die, and then the new people have the new ideas.
So our next conference will be on humility.
or funeral practices of the sciences. So, Mario, thank you for the comment, Mario. Just a quick note. Even with Fred Hoyle, and I quite take your point about Hoyle being, you know, we could say at the very least stubborn to his dying day, decades after the community had moved on from that claim. I take that point. On the other hand, I think you'll agree that his passion for his idea led to a number of things that we now take for granted. And we have a fully fleshed out stellar nucleosynthesis theory because he refused to believe in a Big Bang story and pushed and pushed and pushed, and he was indeed very talented. So what's the balance of that career? We can debate it.
He's one of my heroes.
Yes, no, I think
and he was a genius.
He was a genius, and he was stubborn and very gifted. And I think there's an example of, again, in this instance, of a productive mistake where clinging to one framework led to a number of things that are literally folded into our reigning theory to this day. So again, it's not all one or the other. He introduced the term as a... Yeah, well, that's... Right.
Harry has a quick comment.
It's really just a question about BICEP 2, because my current understanding of BICEP 2, and I'd like you to put me right if I'm wrong, is that the BICEP 2 announcement was premature. that they hadn't got all the Planck results yet, but they decided to go for it. So it kind of wasn't that surprising that it turned out to be wrong, and therefore not that surprising that they were ready to admit they were wrong.
So it was premature, for sure. On the other hand, they made three possible assumptions about the dust and thought that they excluded that possibility with those three assumptions.
Yeah.
It turned out that there was really more dust than even their most pessimistic ideas thought. So
Yeah, and just, I agree again with Mario's comment. Just to say quickly, I have several friends and colleagues on the collaboration. This is one cuts close to home for me. My understanding is that there is not unprecedented in this era of very big, very expensive science, high prestige science, is that there are, often as many barriers to effective collaboration as there are incentives. So there are, indeed still are, Nobel Prizes in the line as well as other accolades that the scientists care deeply about, funding for next generation, this and that. And there were very strong rules about which multinational collaboration was or was not allowed to share data at certain points with people outside the collaboration. Those groups knew they were in a race to the end. And so there's a structuring of the sort, Harry, that you've taught so many of us about for so long. The structure of collaborations and the rules for engagement between large groups has evolved into a very, very complicated ecosystem. And I think the BICEP 2 episode is an example of that, where the Planck team had data that was not yet to be publicly released or shared, and the BICEP 2 team did, I think, as Mario says, careful internal analyses the best they could, but indeed without lacking some of the data they most needed. I mean, it was people racing to get an answer in a very competitive situation where the rules certainly didn't look like the textbook version of scientists looking to share the results and communicate and can't we all get along. It's very, very complicated with these things on the line.
That textbook version of science, just like the cookbook version of science, doesn't actually exist in reality, but it is a very strong public perception of it.
Right.
Yeah.
Okay. Thanks very much. My name is Andrew Goldman. I'm a postdoc at Columbia. It seems to me that anything that appears to be a success today may turn out to be a failure, either because maybe the experiment was done incorrectly or the data will turn out to be wrong within the context of the theory that motivated the experiment, or because future theories may recontextualize or reframe the findings in a way that fundamentally changes the understanding that was original. Okay, given this, in the interim, what are our criteria for success?
Well, this is a good question. So at the moment, and you see in my talk, I talked about the great discovery of September 2015, and subsequently there have been a series of other inspiring binary black holes discovered, and even marvelously an inspiring binary neutron star with an electromagnetic correlate, so they say, anyway. But I could easily find you quite a few physicists working in universities who don't believe any of those results. So one of the extraordinary things, well, this is a part of science which I'm sure is not taught in schools. One of the things that you have to learn is how to decide who's on the fringe and who's not on the fringe. And this is extraordinarily difficult. I mean, we have made a study of this. We made a study of fringe scientists. There's you can find them, you can locate them, they have their meetings and so on and so forth. They don't call themselves fringe scientists, but they have alternative views to most of the other science. For instance, they don't believe the theory of relativity is true. And we discovered that there seemed to be some sort of systematic difference between people who don't believe the theory of relativity is true and others, and that is they have a different value of what Thomas Kuhn, the famous historian of science, called the essential tension. And the essential tension is between people who realize they've got to stick to mainstream orthodoxy if they want to make any progress, and people who think that they have to do Galileo-like radical innovation if they're doing the real science. And the fringe scientists think that sticking to orthodoxy is a bit in for a dig, and what you've really got to be trying to do is invent something brand new all the time. That's the only way to make real progress in science. So you've got to look for these sort of systematic differences. But it's a sort of social skill which you can't teach because we don't really know how we do it, how we decide, okay, I'm going to assign this person to the fringe and not take them seriously any longer. But I've still got to take this person seriously, even though he's, I don't like him very much, but nevertheless, somehow or other, I've got to take them seriously. So it's a very, very difficult answer to that question.
I mean, what you're saying is that the social dynamics of scientific communities are very, very important, and you could look at the social dynamics of other kinds of communities as well to understand success and failure, that science, has particular characteristics, but not so different in many ways from other kinds of expertise and other kinds of professional communities.
Yeah.
Jutta.
Yeah, I think it really also depends on what exactly we mean by failure, because, I mean, there's a more pedestrian understanding of failure, which is relative to a goal. So in the sense that, okay, you want to reach a goal and you cannot reach, you are unable to reach that goal, and so you fail. So, and if you take that as your understanding of failure, then I think error is actually the more interesting term, because when we go back to the roots of error, it's actually erring in the sense of you don't know where you are going. So it's this groping around in the dark, and that is that there is no goal or no, you can't even, you are not even sure where you are. So erring in the sense of not having an understanding of the situation, really.
And that that was what really informed the founders of the National Science Foundation, what they call basic science. And it's something that's not at all encouraged now by science funding, or at least by the writing of proposals. Yes.
Oh, Cornell Green, thefailureguide.com. Interestingly enough, I'm here from a socioeconomic perspective. I'm launching thefailureguide.com next year, and I'm looking to do a podcast series where I interview successful people in business, politics, etc., about a seminal failure in their life. I consider myself, well, actually, I'm a small business consultant in what I call the post-crash economy. If we look at what happened in 2008, it was very obvious that the economy was built on a house of cards, and yet the entire world went along with the subprime mortgage nonsense. And in fact, in the world of business, failure is almost like Voldemort or the Candyman. No one even wants to talk about failure or even acknowledge that it exists. And that's why I'm looking to launch this website and this podcast series, because I work with a lot of startups and entrepreneurs, and failure is something that which is why, forget the rate of how many businesses are going to fail within 5 years or whatever. I find that a lot of businesses don't even get off the starting block, because the concept of encountering that first failure so paralyzes them that they don't even launch. So I'm fascinated to be here and hear you guys discuss, because science seems to be the only discipline that actually acknowledges that failure is even a thing, much less looks at it. But in the context of that, I'd like to ask you guys, in your various disciplines, because you're here because this is the nature of this talk, but within the scientific community, how consciously is failure, the possibility of failure, the probability of it, the fact that it's a possible consequence, really dealt with and acknowledged within the educational aspects and the actual scientific practices and experimental domains?
Catherine, do you want to comment?
About education?
Yeah.
Well, actually, I'm giving a talk tomorrow about...
Yeah. Stay around. You came to the right place.
I'll be here all day, both days.
Sort of a new intervention that we generated from the sort of design thinking mantra of fail early, fail often. So teaching kids that failure can be a good thing. Oh, sorry. So I was just going to say that I'm giving a talk tomorrow about... Sorry. Can you hear me now? Is that better? Okay. I'm giving a talk tomorrow about teaching kids this mantra that comes from design thinking called fail early, fail often, where, when you're in the middle of a task or trying to improve a product or trying to learn, that failure can be a good thing along the way, and you should actually invite it and learn from that mistake. So that's some of the work that I've been doing, but I don't think that failure is really seen as a positive thing in education settings, and in fact, it's, accompanied by lots of negative emotion and learned helplessness and all kinds of negative things. And I think with the current testing craze in education, for example, it's seen as this negative thing, right? Can be indicative of low ability in a failing school. So I think in general, failure is looked on as a very bad thing in education, but
not just in education.
Right, and I think Xiaodong's work obviously speaks directly to this, so maybe she can say more after you, but.
Yeah, Jonathan?
Yes, I'm very interested in hearing your talk, and I'm struck by the parallels between your effort and what we do with our advanced science reporters, which is to encourage them to write about the process of science rather than just focusing on results and press releases. And when you look at the process of science, then you begin to dive into this wonderful ecosystem that includes so much failure and frustration, but it's seen as part of all seen as part of the process. And it's a much richer story than what you get in headlines.
Harry?
I was thinking about this. Now I'm talking about my own career as a sociologist of science. Okay, I've had one really big failure and one small failure. The really big failure founded my career.
Really?
Yeah. And
I'd like to have you on my podcast.
Okay. And the small failure really taught me a lot. Okay, I'll tell you the details later if you like. But I'm just writing a book on methodology, sociological methodology. And what do I say? I say, this is what happened. But sorry, I cannot recommend failure as a good methodology.
Yes. Well, actually, I define failures as first attempts in learning using real experience. So I'm not looking to have a podcast series or a website about failing, but about what failure can provide and particularly getting over failure, getting through failure, and how it can inform us. Certainly, I don't want to teach people how to fail or to embrace failure. That's not the point. But as I said, especially I see in the world of business, people so paralytically avoid failure that they don't even start. They don't even try. Because failure is such a stigma in all aspects of society, no one even wants, especially in business, you can't even admit that you've ever failed.
I think we have a couple more comments.
So, thank you. So I think these comments are really interesting, and something that I think Jutta said in passing at the beginning of her presentation comes to my mind as well, which is that some people in the sciences, let's say, I don't know the other areas you described so well, but some people are at a career stage where they're sort of allowed to fail, and that's often not the case for young students. Undergraduates probably can fail a lot because it's still a kind of safe environment. Grad students probably can't. Postdocs certainly can't because of the extraordinary pressures on the field for those who are seeking a certain kind of academic position, of which there are very, very few and many people seeking them. And so Harry was lucky that he could fail early and it turned out okay, but I think that's not going to be true for most people starting out at this stage. So that highlights, to my mind, again, a distinction between a kind of individual researcher or a small group and sort of the community. So in some of my work, I was really fascinated by individuals who could fail in these, I think, very productive ways, where the whole community has learned enormously consequential things from the fact that they were wrong on these very interesting, hard questions. That didn't always pay off well for the people who were wrong. It paid off for the community. We now know an enormous amount that we collectively did not know before, but that doesn't always redound to the benefit of those who helped us learn that. And so there is, again, I think, a question of a kind of a life course for an individual and even for whole fields or subfields that I think it's helpful to keep in mind, that kind of bouncing between sort of small individual or small group and something like the community larger. And there can be benefits to one without benefits to the other.
Jutta?
Just very quickly, I've done some interviews with scientists. My postdoc did a lot of interviews with scientists, and there was nobody who had anything positive to say about failing or was even aware of the kind of day-to-day failures that we've been talking about. So that doesn't seem to be widely known in the scientific community.
Thank you all so much.
Hi, Xiaodong Lin from Teachers College and Cognitive Science. So what interests me is that when you guys were talking about all these different scientists from historical perspective, there's something missing there, I feel, is emotion. And it feels to me, because I have been developing stories about Einstein, Curie, and all these struggle stories for children all the past 5 years with NSF. So I was struggling by, actually it's very emotional. And this is everybody, when things didn't work out, they say, sucks, But from your data, I feel like they're so cool. This, oh, it doesn't work out great. This doesn't work out wonderful. Maybe it's like that. But I'm just talking about one emotion issues related to failure, because that's the area I think generates all kinds of emotions. And that's why a lot of the Nobel laureates cry when they got awards, because there's so many, sweet and sour feelings come out. And the other one is strategy. So do they all use the similar strategies across all three different cases? So, and then I'm also wondering with children that I work with, shall we reveal the emotional things to the teenagers when they are already emotional cooling with all the girls and the boys and all the images and perceptions? So shall we reveal the scientists' emotions and to the teenagers when we educate them about failure?
Thank you. That's a fascinating point. So I think one thing that historians and sociologists and philosophers have the great luxury to get to do is actually to immerse ourselves to the best that we can in a kind of affective or emotive world of these researchers, because because we do have we're trying to understand at some level the kind of human experience and human practice, and that is, as you say, often quite rife with emotion. These people are often extraordinarily passionate. And I think that feeds some of what might be seen as stubbornness later on, those who won't let go. It's seen as the rivalries and the race for this or that result, let alone accolade. So I think you're quite right to see, not just today, but indeed for almost any epoch in the history of science that we've looked at, and Pamela's work will speak as well to this from the early modern period as the most recent studies, that these activities the people who do them are often extraordinarily passionate. This is a question of what gets you out of bed in the morning and what do you stay up late at night thinking about. And that's as true for Galileo as for the members of Bicep 2 and everything in between. And so one thing that I find very interesting is in a recent turn in the last few years, maybe a decade or so, of ways to try to communicate about science with large audiences of non-scientists, away from a kind of merely or predominantly didactic mode, let me teach the content or teach the results, and not so much only to teach the method, but to teach to share something like the subjective affective experience. And there are many ways this comes up. There are podcasts and live monologues and all these wonderful things like Story Collider that some people here have participated in. And what's really fascinating to me when I put my historian's cap back on is the efflorescence of kind of available moments where scientists allow themselves to be seen as really very sharing subjective experience. They are subject to the whims of human passions and can fail and feel it very deeply. But what does that portray about the nature of science as a kind of larger communal established machine for producing reliable knowledge? So I think there's an interesting tension between the passions of the individual and something like one hopes the reliability or the solidity of a kind of broadly shared product at the end. And I think there's an interesting tension that we can play with or wonder about between the kind of individual hopes, dreams, fears, failures, crashes, and successes, and something like a set of systems or structures that might be bigger than all of that. And I think that's something that's, I think, an interesting moment to think through in the United States politically right now and so on.
I'll save time to others.
I guess I'm next. My name's Tim Wu. I guess I describe myself as a failed scientist. Used to be in biochemistry, got picked up. So I make my living at the law school now instead as professor. And I have but my first pursuit in life was science. I'm on plan B or maybe plan C here. But I had a question, really I think for Harry. Is your name Harry, is that right? Yeah. I had a question. I was very interested in your discussion of the fringe and the core. One of the things I'm interested in is the history of innovation, technological innovation, which is related, not quite the same as I think the history of science. And there's an interesting debate, or I guess, I don't know if debate's the right word, but there's two types of innovation that you tend to see. One, maybe at the core or not at the fringe, so large firm innovation, the classic model being Bell Laboratories, or maybe even today at Microsoft or Google or something. Where the advantage of that kind of invention or innovation is enormous resources, a very talented, usually the best people, or many of the best people. and then often in history people said, well, that's obviously where things are going to happen. But then historical record, there really are, at least in technology, examples of people, I don't know the fringe, but at least not, fringe might be one word, but at least outside the big companies doing the most significant things. The invention of the telephone, maybe the invention, I don't know how you want to count Google, invention of radio, FM radio, things like this here at Columbia. And they're not always like way in the fringe. They're not completely insane, but a little outside. And the big firms have this challenge that they're often cognitively, even though they have resource advantages, they have some cognitive limits. They're often trying to improve on what's there slightly, or they have the problem that the funder is not interested in things that might challenge the revenue model. This is a big problem for Bell over the 20th century, is they'd invent things and then Bell would bury them because they wouldn't fit the business model. So I wonder if there's a similar kind of, I bet you would know more about this, about the kind of core versus fringe in science, and whether, in fact, significant discoveries do happen at the fringe occasionally, or whether they never do, and where things are today. I'm just curious about this.
Well, I never thought about this before, yeah, but it's interesting. Yeah, I would have thought there's a very strong parallel, and this notion of the essential tension probably applies just as much in business. Remember, Google and everybody else started off as the radical innovation in somebody, and the Apple in the back of in the garage and all that kind of thing. Right,
Apple being the other. Yeah, Apple being the other great example. But are things ever discovered by fringe scientists?
Oh yes.
Yeah. Okay.
Yeah. And the thing is this: I say that the thing about the fringe is that the balance is different in how they choose what's valuable. But nevertheless, I'm sure that for science to proceed, it's got to have a few people who are, or quite a few people, who are in the crazy side of the fringe. Well, David was talking about the people on the quantum theory. You've got to have those people. Very few of them will succeed. Very few of them indeed. But some of them will, and they're absolutely vital.
I agree. Now, just to say very briefly, one of the things that fascinated me by the group that I wound up writing about was something, they were neither all the way out nor all the way in this sort of center-periphery model, which again, I actually take very much from Harry's work. That they were, the people I wrote about had PhDs from elite programs in physics and were not pursuing traditional career paths in traditional institutions. So they had a kind of disciplined curiosity, if we can coin something like that. That they had they were aware of the tools, the chops, the way to pose questions, and they were open to a wider range of often pretty bizarre sounding questions that were not being pursued in the mainstream center. So it was that, again, maybe that's the tension that you described. They were neither all in nor all out. They could speak in a profitable way with experts in the center, and they also weren't, so to speak, limited by that set of questions or institutional prerogatives. And that's I don't know how you engineer that on purpose. We can find examples from history. I'm not sure if there's a recipe for that moving forward.
I wonder if looking at the RAND Corporation or a think tank like that was really trying to innovate quite self-consciously, whether that would give some insight into those dynamics.
Can I just say one more thing, which I kind of forgot to say when I was saying the first thing? I think, science is often held up as a sort of thing that's in opposition to religion. But actually, I think it would be more, it's better off to think of it as a kind of religion. Because the thing that the fringe scientists are going to have to do, since most of them are going to fail, is just hope that what they do will be recognised in a later life, even if they don't succeed in this life, And that's part of it, and maybe that applies into.
I make one last comment. You don't have to respond to this, but it is. People have been saying, "Well, failure is always demonized." In Silicon Valley, where I spent some of my career, there is the attitude, whether you take it seriously or not, is a little bit different, at least in people's actions. People brag about failure being their badge of achievement or something, and it's sort of honorable to brag about some. It's honorable so long as you succeeded afterwards. The guy who failed and never went anywhere, that not a little less honorable. But most people get up there and talk about how they failed at something anyway.
Yeah, I think it's less useful to talk about religion than to talk about a discipline, a professional discipline. I think that idea of disciplined curiosity is really telling. Anyway, moving on.
Thank you very much. My name is Anne-Sophie Bauwich. I'm a postdoc here, and I would like to go to the question about retrospective failure, because there was kind of the agreement here, and I'm not so quite sure about that. So the question is like, well, how would you, for instance, evaluate failures today? And I think we might want to look at a different epistemology, because Harry Collins here said, for instance, that, well, there's a lot of social differences in how we conceive of science, and we need kind of a certain amount of fringe scientists. But that comes back to Andrew's question earlier about success. I think we need to think differently about success when we talk about ongoing science rather than past science. Our epistemology is framed by, like, the history of science, the philosophy of science frames epistemology on past episodes. And I wonder, to what extent would our idea of success be different if we look at ongoing science, where we are not sure whether an explanation is correct, where the criterion of success is perhaps more the way it propels science by asking new questions that are somehow opening up new doors to new technologies, to integration. There could be different kind of criteria. And maybe the same holds for failure. So seemingly successful explanations are failures because they don't propel anything. They're just kind of data accommodation in a kind of an underdetermination sense. I was wondering what you make of that.
Well, I'll just say something very, very briefly. I don't know what to make of it, but one can practice, one can work out what one might make of it by thinking about string theory. Is it a success or a failure?
Some people would say it's a religion. I talked to one who actually left it. He's a physicist in recovery.
Yes, but that's a great example as well, because the original claim, maybe this comes back to something you two were saying, the original goals announced by the early proponents of string theory have clearly not been borne out, and I think even the proponents will agree on that. On the other hand, there have been all these unanticipated sort of productive collaborations outside that original course of study, because mathematical techniques developed in the pursuit of one thing have turned out to have all kinds of very productive roles to play in neighboring areas. So is that a success or a failure? It's a tool, it's a technology that's turned out to be much more malleable, plastic, and indeed generative than originally foreseen, even if the kind of religious-sounding original goals for many of these proponents have not yet been borne out. So maybe that goes to your point. This is propelling certain kinds of inquiry that have been stalled out in their own terms for decades in other areas of physics, in this case, and mathematics. So I wouldn't want to say, I wish we never had string theory at all, even if I am ambivalent about the claims of many of its strongest proponents, because it has had, we might call them spin-offs in a kind of Silicon Valley language. It has spun off incredibly productive techniques in neighboring areas that really have gotten through log jams in other domains. And I think that's something to be lauded as well.
Go ahead. Well, just a very brief and perhaps obvious comment on that. I mean, I think that the way the question was posed, it was probably too broad, because there are, as we've seen, so many different notions of failure and success around that, depending on what you mean by these different concepts. I mean, whether you're talking about psychological issue, whether you're talking about personal successes or personal failures, or whether there is a sense in which we can even abstract from the personal or from the sociological notion of failure and just, or success, and say something about, oh, this, idea was successful depending on, independent of who had it. I think these are all questions that we have to answer before we can even start to frame the question or to ask the question that you asked.
Let me just say that in the Center for Science and Society, we are actually conducting an experiment on this in our Society and Neuroscience program. We have postdocs like Anne-Sophie who are working in labs. So Anne-Sophie is a historian and philosopher of science, and she is working in Stuart's olfaction lab and a neuroscience lab.
Failing successfully.
And one of the really interesting things that she's studying are dead ends in olfaction research. We can call them that for shorthand, I hope. And looking at these dead ends that in some cases are being resuscitated now is quite interesting in terms of real-time study of very current cutting-edge science. So I think that there are really interesting ways in which this can be figured out by having historians and philosophers of science, sociologists of science, really embedded in labs. Thank you.
Thank you all for your remarks. Katie Tabb, I'm in the philosophy department here. I'm noticing a tension between the conceit of the conference seems to be that we can consider failure as something like an epistemic virtue, something that will be beneficial and military for science. But then for the individual scientist, it seems very painful. So you said you've done these interviews and no one's happy about it personally, which of course makes sense. And so I was wondering if you could speak to how this kind of tension plays out in terms of how we think of science as a collaborative enterprise, because it seems like it introduces real antagonism between the individual scientist and their community when we look at sort of the long arc of scientific progress.
Mm-hmm. Jutta, did you want to say something?
I have to think about it for a minute.
Mm-hmm. I think that that's a really, interesting question. It really speaks to your, your question, David, about how you can really reconcile the kind of personal, biography, history of science with science as a social activity. And I don't know the answer to it, but I think that they are at odds. I mean, and that is a challenge, I think, for historians and sociologists of science.
Yeah, part of the reason I ask is because this seems lacking from the kind of traditional stories we tell about the nature of scientific progress, in which collaboration, we've moved away from like the old single-souled genius model to this collaborative, productive model. And I feel like this piece is really missing. So I'm wondering kind of how we need to retell those stories in light of what you've been saying.
I mean, one thing is, I think that we can see when in the scientific community, when we talk to scientists, that there are different kinds of collaboration in the sense of some collaborations are suggested by the topic that people are working on, and it's clear that you need to have different people with different expertise to work on this, and this is where collaboration is something that's considered positive, but then there's the expectation that you work together that comes from the outside. Yeah. So it's kind of extrinsic force. And then collaboration is not perceived as something that is positive, and that, I think, also impacts thinking about, what do I consider as a success for myself or for the group, and what do I consider a failure for myself or for the group, depending on what kind of collaboration I would be in.
Thank you.
So I'd wonder if you can get any, I've never thought about this before, but I'm wondering if you could get anywhere, once again, by thinking about the analogy with religion, which is par excellence something where terrible pain is normally thought to be a precursor to success.
So scientific martyrdom.
Thank you. Please.
Hi, good afternoon, or good morning. My name is Henry Nass. I'm wondering, the U.S. patent system is now up to 9.6 million inventions, patented inventions, most of which never got produced, and gone to market. And I'm just wondering if that might be a very productive base to look for or to study failure in. And for instance, I have a patent called, it's not mine, Hurricane Dissipation System and Method. That was just issued in 2017. And of course, it was issued even before the hurricanes we had big destruction from. But I think this will never be produced either. And a second patent I might mention is one that apparently was a failure when it was invented and while it was in patent, but at least made a fortune soon after, and that's the fidget spinner, which you might remember. Okay. So is looking at the patent inventors database really a ripe core for study of this stuff?
Yeah, Tim.
I'll answer that.
Good.
I think patents are sought after for completely different reasons than big products. Strategic reasons.
Yeah.
They want to have a big portfolio. Honor, it feels like a reward to get a big
You have to understand the patent system, basically. Yeah. I wonder if patent systems differ in different countries, different nations. Presumably there might not be that kind of possibility in other places. I don't know. Interesting question. Stuart, last word.
I'm gonna make this quick then because we're
Don't
almost
fail.
out of time. But I actually really just wanted to reiterate something that was brought up first by Andrew and then again by Anne, and its notion that if we think failure is retrospective, we should think success is only retrospective as well. And I'm reminded in particular, maybe this is the way to end the panel, on a wonderful quote from John Maddox, the longtime editor of Nature, who was once asked by a reporter, so how many things do you think Nature publishes that turn out to be wrong? And Maddox said, oh, well, that's easy, all of them. And of course, many of us having tried to publish in Nature would agree with that. But I think that's an important point, is that many times we think only failure is useful, can be explained or examined retrospectively or judged retrospectively. But I think success also really, we just have this pejorative sense that failure is one thing and success is another. It's harder to judge success retrospectively. I'd say, along with Anne, that the important principle is progress. And if you make progress with failure, you make progress with success. Progress is the issue, really.
So that's a good way to end, because the question is, what is progress? That is a question that I talk to my undergraduates about a lot, and that is presumably a question that's going to be raised in the next session, which starts at 11:30, failures of social regulation. So please stay around for that, because I think will get at the question which I didn't have a chance to raise, which is what kinds of implications of these incredibly expensive failures, and even if success, is made through them. So right now, though, let's thank all of our speakers and respondents.